Hey there, math fans. Going to talk about the Farey sequence again. Watch my previous video if you haven't already about this idea of finding fractions with small denominators that are closer and closer to some value. I actually already filled this in. We talked about how these are all the fractions with denominators up to 5 that are reduced. And this clever observation that if you want the next smallest denominator nearby, you add the numerators and you add the denominators. Quite surprising. And you can just keep going. So, and I'm going to do this in a future video when I'm talking about batting averages. But anyways, this would be 3/8 would be the next one you'd get in here. Add the numerators, add the denominators. And I did a visual of that. There are several things related to this, kind of a large number of things related to this concept. But one that I hadn't really seen before was this concept of what are called Ford circles. There was a mathematician, I think it said early 1900s. Farey wrote about this. I'm going to show you the history in a second. In 1816, so this idea of approximate fractions is pretty old, and some of those concepts were from before that too. But there was this observation that if you plot your circles so that their centers are above these points, and you do it in a certain way, you can get a bunch of tangent circles. Now, the history of studying tangent circles is old. There's this thing called Apollonian gasket, where it's a fractal where you continue to remove circles. And I'm going to show you something like that in just a second that's related to this. And that's related to circle packing, which I've talked about in other videos. But that was a Greek mathematician, Apollonian. Anyways, I'm going to show you this here, and then I'm going to talk about the history, and then I'll move on past this. Okay, so here's my version of this. Again, I wanted to make it, but some of these visuals are going to take more work than I was quite ready for. So I'm just going to show you. So what I'm going to do is down below, I'm going to get it running here so that you can see. Maybe I'll do this, which I've already shown you, the first few fractions. So currently I have 0 and 1. Now let's put in the halves, and let's put in the thirds. That's a little bit faster than before. I paused it now. Above, I'm going to draw a circle. Now the radius of that circle is related to the denominator and fraction. If you want to know more, you can look up Ford circles. But I'm going to send this going. So what I'm about to do is draw some more circles. So I'm going to draw a circle that's above 0. And I'm also going to draw a circle that's above those other two fractions. So let's let that go for a second. Circle. So there's the one that's above a half. And I made it tangent. Now I'm going to draw another one that's above a third and 2/3. That's that one, and it's tangent. Turns out it's mutually tangent. So it has this kind of surprising connection. You'd have to read up on that, how they prove that, and what the radius is, and how you draw it. The radius, is 1 over the denominator, 2 times the denominator squared. This actually is really important in the study of irrational numbers and how do you approximate numbers. But that's a story for another day. All right, so let's get it going here. Let's plot them both as we go. So I'm going to plot more and more and more circles. And right below them, you're going to see me also plot the Farey sequence. And it's this fractal pattern that goes on forever. So if we just let it keep going, we can zoom in here and see that it just keeps going. They're tangent forever. It will just keep drawing. Now, my computer's going to slow down because it has trouble keeping up. But it's going to keep drawing these. So that's pretty cool. Maybe I'll reset it so you can see it in action. It's drawing so many that it has trouble keeping up, but there we go. And then it keeps drawing. So I thought that was pretty interesting if you've never seen that before. And then there have been many visuals made relating to this. Okay, so a little bit of history, just because I like to throw this in here. If I'm going to look up this information, I'd like to know where it all came from. So 1816, I actually found the article. It's very short. It's always amazing that these big things sometimes come from, a short little observation. So this was in so it's a British magazine, 1816. He said, I've noticed some curious fractions. I liked the title was on a curious property of vulgar fractions. Now, vulgar, I looked it up. In British, it means common. So it didn't. It derives from a word, a Greek word, I think it said, that means common, or Latin word. I wrote that somewhere. Yeah, Latin word. Crude or common. Okay, so he says, I've seen this property, and wrote a little kind of page and a half on this. So here's what it said. If all of those with the greatest and on their lowest terms does not exceed any given number, so he's talking about the denominator not exceeding a given number. I just like that we can relate to this. This is someone that lived, a couple centuries ago, and we can communicate with them. Okay. So he wrote down those first few, just like I did in my video. And then he talked about this observation. Didn't prove anything. This wasn't a mathematician. It was just a geologist that observed this thing. And he said, if you just add the numerator and denominator, I'm kind of curious how he was able to typeset that. You get the following. This add the numerators and denominators. Fact. He did add the numerators and denominators of 1/5 and 1/3, which are not adjacent so we wouldn't be adding those, but an interesting little piece. And that was page 1. Page 2 is just a little bit longer. Was just a few more words. But he keeps going and does some slightly larger numbers, adds the numerators and denominators. He says, I'm not acquainted with this property, or whether it's easy to demonstrate. Your obedient, humble servant. This mathematician, Cauchy, who was a British mathematician at the time, read that article, wrote about it, and attributed this fact to Farey. And that's why it's called Farey sequence, that little bit of that's observation he made. Which is all right, I feel like, even if he didn't analyze it. So I looked up vulgar fractions. I have a few little things to say and show you. Just to wrap up. So if they are indeed neighbors, so they define neighbors in kind of a curious way here. But neighbors, if when you subtract them, you get 1 over the product of the denominators. So we would say these two are neighbors in that sense. And we use them to put together the 3/4. Because if you do, how do they write it? BC minus AD, you get 1. Now BC would be, I'm trying to use the same symbolism they use, 1 times 2, this sort of cross multiplying, and 3 times 1. Did I do it in the same order? Maybe not, because I'm getting -1. I think typically it's written this way. But it's because I did the wrong order that I didn't get what they had. So that's an interesting property, and it implies that the distance between neighbors is always 1 over the product. And that's useful in terms of approximations. Like if you're approximating a number by some fraction, a over b, you sometimes can say something about it being bigger or smaller than something over b squared, or something related to b squared. And it often has to do with this fact that the distance between them is 1 over this product. And people use this to prove facts about rational numbers and irrational numbers. I have a whole book about that. I'm starting to see this connection between this sequence and these ideas. Now, a few other things I found, and sorry that I'm scrolling here. I'm just going to pull this up, and then I think we'll end here. The number of Farey sequences at a given level, you actually can talk about, because it has to do with the number of things that are, this is called the Euler-Totient function, the number of things that are relatively prime to a given number. That has to do with when can you reduce. So if you're talking about like a sixth, and you have 1/6 and 2/6 and 3/6 and 4/6 and 5/6, these would not contribute new fractions to the Farey sequence because they'd already be in there. This would be in there as a third. This would be in there as a half. This would be in there as 2/3. And so we would say that 1 and 5 are the only numbers that are coprime to 6. And we have this function that says, well, how many numbers are like that? There's 2 of them. That's what this number is. So that's what you get. There are well-known what we call asymptotics for this, which tells us at a given row in the Farey sequence, there's going to be about 3 over 9. So about a third n squared. Anyways, and I noted. So it was 1938 that Lester Ford. Okay, so there you go. There's a little bit more history on those fractions. There's even more to say about continued fractions, how we approximate. But this is enough. I wanted to do this before I actually got to the baseball stuff I wanted to say. We needed this sense of how do we approximate things with small denominators. Now in baseball, if you're computing batting averages, the most number of at-bats ever was around 700. But most players don't get much above 500. So if you're only allowing denominators up to 500, you're basically only considering the Farey sequence up to when the denominators get to 500 and never beyond. That allows you to get nearly every batting average, but some are going to be really rare because some only occur a few times. So I'll talk about that as a side topic, but that's what got me thinking about this in the first place. All right, thanks for listening.